In lecture 11, we're going to talk about carboxylic acids and their derivatives. Some quick overview of the structural and physical properties of carboxylic acids. The carboxylic acid functional group is the carbonyl, where the carbonyl carbon is attached to an OH group. This is kind of like the combination of a carbonyl and an alcohol, but specifically when they're together, it's a carboxylic acid. The structure that the book shows here shows a bit of a strained 120-degree sp2 hybridized carbon. The only reason why these angles are not as close to 120 as we might hope is because this is a hydrogen instead of a methyl or some other R group. Because of this being a hydrogen, the hydrogen bond, specifically hydrogen carbon to oxygen angle, is smaller than we would normally think. If there's an R group there, these angles balance out to be about 120 degrees. Bond lengths are pretty typical. We've got a standard bond length, 1.2 angstroms carbonyl. In this case, there's a hydrogen that's going to be a standard approximately 1.1 angstrom carbon-hydrogen bond. We've got a slightly elongated carbon-oxygen bond, and then a very short hydrogen-oxygen bond. Remember that in the carboxylic acid, it's this hydrogen that's easily removed, and so that bond is shortened because it's weak. There are two resonance contributors to most structures of carboxylic acids. Here are the two resonance contributors to the neutral carboxylic acid, where we can take the electrons from the single bond O, make it a double bond, and take the electrons from a double bond O, make it a single bond. This is a good indication that this hydrogen on our normally what we think of as our single bonded oxygen is easily removed because the resonance contribution puts some positive charge on that oxygen, and that oxygen therefore wants to get a pair of electrons back. It can most easily do that from its hydrogen. Carboxylic acids are hydrogen bonding. This is an example of a hydrogen bonded acid dimer, where you can see that there's a donor from the hydrogen to the carbonyl oxygen, and vice versa, the donor from that molecule's hydrogen to the other molecule's carbonyl oxygen. We can see that they are hydrogen bonded simply by looking at their properties. Comparing something like propionaldehyde or propanal and its boiling point, 49 degrees Celsius, this is not a hydrogen bonding molecule. It can accept a hydrogen bond from some other hydrogen bonding molecule to the carbonyl oxygen, but propionaldehyde by itself cannot hydrogen bond because it does not have a hydrogen bond donor. Propanol, however, does have that hydrogen bonding donor, that polar hydrogen, and acetic acid also has that hydrogen bonding donor, that acidic hydrogen. So you can see the very clear difference between a hydrogen bonding molecule with strong intermolecular forces boiling around 100 and higher, and a non-hydrogen bonding molecule, something that only has dipole-dipole interactions boiling at 50 degrees Celsius. Of course, the carboxylic acids, like we mentioned, are acidic compared to an alcohol whose pKa is about 16. The normal typical carboxylic acid will have a pKa of around 5. That's 10 to the 11 time more acidic than an alcohol. Now, again, the reason that an alcohol is acidic at all in the first place is because removal of that hydrogen as H plus produces a negative charge on an oxygen, which is relatively stable. But with the carboxylic acid, removal of its hydrogen puts a negative charge onto the oxygen, which is resonance stabilized. We call that anion a carboxylate. The negative ion of a carboxylic acid, we call it carboxylate. So that's clearly, you can see the difference between a non-resonance stabilized oxygen and a resonance stabilized oxygen. The effect that that has on the willingness to form that negative charge is a factor of 10 to the 11th power. This is, of course, a picture of that orbital delocalization, the idea that the fact that these electrons can be delocalized from one oxygen to the other means that these orbitals are conjugated and the electron density is smeared out among the carbon and its two oxygens. A visual picture of the energy The idea that if we have a neutral alcohol or a neutral carboxylic acid in water, those are roughly the same energy, but once we do a proton transfer, we get a more stabilized O. That's resonance stabilized, that's a lower energy. And you've got a higher energy O that's non-resonance stabilized, it's a higher energy. You can see the difference in energy between the non-stabilized and the stabilized O. Nomenclature for carboxylic acids is relatively simple. The generic name is alkanoic acid. It's the carbon chain numbered from the carboxylic acid carbon, and we add oic acid to the end of that. So a single carbon carboxylic acid would be methanoic acid, a 2-carbon carboxylic acid, ethanoic acid. Here's a 4-carbon carboxylic acid, butanoic acid. Here's a pentanoic acid and another butanoic acid. Here's another butanoic acid. Of course, since the carboxylic acid is such a high priority group, having 3 bonds to oxygen, so 3 heavy atom bonds attached to it, it has a high priority, and in the case of a carboxylic acid, will number from the carboxylic acid carbon, similar to the way that we numbered from the aldehyde carbon when we were naming aldehydes. So this is the 1 carbon, so we could have a 2-cyclohexyl propanoic acid. In this case, we have a propyl group off of our 2 carbon and a ketone on our 3rd carbon. So because we've got 2 functional groups, we could name this as the ketone with the carboxylic acid as a substituent, or we can name this as a carboxylic acid with the ketone as a substituent. It's easier to name the carboxylic acid as the root with the ketone as a substituent, and we would do that anyway because the carboxylic acid is the higher priority. So we'll make that part of the root. So I referenced this before, but naming ketones as substituents, you call them oxo groups. So this is a 3-oxo with a 2-propyl butanoic acid. Now you could ask, why don't we make the propyl group part of the main chain? Well, you absolutely could. That would be a pentanoic acid, 1, 2, 3, 4, 5. Then we need to know some way to name this ketone, ethyl ketone group, as a substituent. And we really haven't seen that yet. You could call it an acetyl group if you wanted to, but generally speaking, we can be flexible in this naming. We want to put the oxo and the carboxylic acid on the same chain. We'd make that a 4-carbon chain with a propyl group coming off of it. Here we've got a butanoic acid with an amino on the 4th. That would be 4-amino-butanoic acid. In the olden days, they named these as alpha, beta, gamma. The positions adjacent to a functional group were named off as alpha, beta, gamma, delta, etc. So instead of calling this 4-aminobutanoic acid, you could call it gamma-aminobutanoic acid. So you have the amino on the gamma carbon. This GABA, gamma-aminobutanoic acid, GABA is a common neurotransmitter. You might have heard of GABA before. Notice that these in the common names, they're using butyric acid or propionic acid or valeric acid. Those are the common names for, say, a butanoic acid was butyric. Valeric acid was the pentanoic, the 5-carbon chain. Here they're saying it's an alpha acetyl valeric acid because they're putting this acetyl group on the alpha carbon of a 5-carbon chain. Here's propionic acid, acetic acid, formic acid. Don't worry about the common names. If you see them, you might recognize what they are. Valeric is 5, butyric is 4, propionic is 3. Those aren't too hard to remember. But as far as what I care about in this class and what ACS cares about, the common name is ignored. IUPAC is what we care about. Sometimes, though, acetic acid is used. We use acetic acid a lot as a common name and formic acid a lot as a common name. Groups attached to carboxylic acids can highly influence their acidity. You see that compared to normal acetic acid, which is a pKa of around 4.7, chloroacetic acid takes our pKa down to 2.8, dichloro down to 1.2, and the trichloro down to 0.64. Remember, lower pKa means a stronger acid, so putting these withdrawing groups on the acids are making them more willing to give up their hydrogen. That's easily explained because the negative charge that results from losing the hydrogen, so we can think about the conjugate base, is stabilized by the chlorine's ability to delocalize that negative charge further throughout the molecule. The withdrawing group is not just the carbonyl. We now have chlorines to do that. And the more chlorines we have, the greater that withdrawing effect, the greater the stabilization, and therefore the more stable the conjugate base, the stronger the acid. You can also see that with proximity. From 4-chlorobutanoic acid is only a little bit stronger than regular acetic acid. As we move that chloro group from the 4 to the 3 to the 2, we see we go our pKa from 4.5 to 4 to 2.86. So the proximity of the withdrawing group is also a factor. What we learned about NMR for deshielding and the proximity of electron withdrawing groups to remove electron density from a certain atom, that should not be surprising at this point. There's also an interesting trend for aromatic carboxylic acid, so a benzoic acid, and electron donating or electron withdrawing groups on the ring. Generally speaking, since an electron withdrawing group pulls electron density through the ring, that should have the same stabilization effects on the conjugate base as we saw with these chlorines. So something like a meta-nitro or a para-nitro or an ortho-nitro, those are much stronger than regular benzoic acid. On the other hand, since a donating group would push electron density into the ring and increase the electron density on our negative O in the conjugate base, you can see that the donating group actually weakens the acid. Paramethoxy with the donating group is a worse acid than regular benzoic acid. So the withdrawing groups have that effect of stabilizing the negative charge on the conjugate base. Now notice that meta versus para versus ortho, the position actually matters. Ortho is the strongest stabilizer of the conjugate base. Meta and para are extremely close. So what's going on with ortho? Well, as I say here, this is a combination of resonance and inductive effects. We know what the resonance effects are. If you want to go back and look at the electrophilic aromatic substitution chapter, you can see how resonance structures that are caused by substituents on the ring can affect the electron density on the carbons around the ring. And so it should make sense that resonance is a major effect. But let's look at induction as well. Here's a slide I have from older class, but you can see a normal benzoic acid at 4.2. If you put a withdrawing group like a fluorine, 4.1 in the para, 3.9 in the meta, 3.3 in the ortho, putting the group closer to the thing that it stabilizes, in this case, the carboxylate, should increase its effectiveness at withdrawing electron density through the ring. Now remember, fluorine is not a pi withdrawing group. It is a sigma withdrawing group. So what we're talking about here are not pi effects, but sigma inductive effects. So these are weaker. You can see it's not a dramatic change in pKa. It's about 1 unit, so about 10 factor of 10. And the closer that group is, the more dramatic it is. If we have a pi withdrawing group, like a nitro group, again, we have strong resonance effects in all cases. But the closer that group is to our conjugate base negative charge, the way more stabilization we get. Again, and that is the same thing as we saw with the fluorine. Putting the nitro group closer to our group, we get strong inductive effects. Whereas when we put the nitro group far away from our group, we get weak inductive effects. But we have resonance in all cases. Now, Here they say meta is mostly inductive. If you go through and work out where the positive charge ends up, our positive charges always end up ortho to our carboxylic acid group, as opposed to with the para and ortho, the positive charges end up on the ring carbon attached to the carbonyl. So you miss a lot of those resonance stabilizing effects when you have the withdrawing group in the meta position. We've seen many ways already throughout the previous chapters in this course involving synthesis and reactions of carboxylic acids. For example, we've seen oxidation of primary alcohols to carboxylic acids using sodium chromate, chromic acid, or KMNO4. Remember, those are the strong oxidizing agents that bypassed the aldehyde intermediate, basically accomplished two oxidation steps at once. We also saw cleavage of alkenes using concentrated KMNO4 in the event that one of our alkene carbons was not substituted and we had a hydrogen there. That cleavage of the double bond would result in a carboxylic acid on that side. We've also seen cleavage of alkynes using KMNO4 concentrated. Again, that makes the dicarbonyl that's not isolated, which then cleaves to give the carboxylic acids. Here, the book is throwing in an alternate method. You could use ozone with, instead of DMS as your second step, you can use water, or sometimes you use hydrogen peroxide. That's another method. It's a slightly more oxidizing conditions for ozone. But either way, you can cleave the alkyne to get the carboxylic acids. It turns out that side chains of alkyl benzenes are relatively easily oxidized using any of our strong oxidizing agents, like sodium chromate or KMNO4. What we mean by this is that we've got some ring with an alkyl group, so methyl or ethyl or propyl or something like that, that whole side chain is easily cleaved off except for the last carbon. The last carbon remains attached to the ring and it turns into a carboxylic acid. This notation with the Z, with the line through the ring, means that we are indicating that there is some other group that we're going to call Z attached some other place on the ring. We're just not specifying where on the ring it is. It could be ortho, meta, or para to the alkyl group. That does not matter. But what does matter is that Z has to be oxidation resistant, because if there is anything else on the ring that's oxidizable, like an alcohol, for example, it will get oxidized by these strongly oxidizing agents as well. We can make carboxylic acids by adding a single carbon electrophile to a Grignard. We can get a single carbon electrophile in a Grignard reaction by using carbon dioxide as our electrophile. If we take our alkyl halide, make a Grignard out of it, we have RMGX, have our Grignard attack carbon dioxide, that will kick the electrons up onto the one of the oxygens. We have now added a C double bond O, single bond O to our R group. After protonation, that gets us our carboxylic acid. Here's an example. You can see if we start with, say, bromocyclohexane, a 6-membered ring, turn it into a Grignard, add our carbon dioxide electrophile, we end up with the carboxylate, and they add the acid, we add a single carbon carboxylic acid to our ring. It's a convenient way to add just the carboxylic acid group to some alkyl skeleton. We can do a similar process using nitriles, which we will then hydrolyze. Remember that nitriles, the C triple bond N cyanide group, is a good nucleophile. We can displace some alkyl halide as an SN2 reaction, and then hydrolyze the C triple bond N into the C double bond OH. I'll show you that mechanism on a couple slides. Notice in the example here, if we start with, say, benzyl bromide, displace the bromide with our nitrile, and then hydrolyze the nitrile to the carboxylic acid, we essentially get the same thing. The carbonyl carbon in the carboxylic acid is the carbon that we add to our molecule. In this case, the carbon that we're adding to our molecule, we're adding as a nucleophile, whereas in the previous synthesis, we were adding our new carbon as an electrophile. Here's the mechanism for the hydrolysis of nitriles. We have the ability to do this in acid or base conditions. I have these slides again from an older class here, but I also posted the note on hydrolysis of nitriles with the mechanism in our Canvas course. The hydrolysis begins with protonation of the nitrile, the same way that we might protonate a carbonyl. That gets us a resonance stabilized carbocation, where the water, that is the conjugate base of our acid, can attack the carbonyl carbon. It's not a carbonyl carbon, but it's like a carbonyl. That will get us our water on our molecule, which we can then do a proton transfer onto our nitrogen. That gets us another resonance stabilized carbocation. We can add another molecule of water, do another proton transfer. This is, by the way, called the carbanolamine. In this case, it's a protonated carbanolamine. We can then, after doing that proton transfer, we'll have NH3 plus. That's a good leaving group. So we can displace the leaving group by regenerating our carbonyl from one of the alcohol oxygens. That will get us our carbonyl on one O, our alcohol on the other O. If we transfer the H plus off of the carbonyl, we get our carboxylic acid. So you can see that we basically, from our nitrile carbon, add two waters, and those waters end up being our carbonyl and our alcohol OH, and then the N that's triple bonded ends up getting displaced as NH4+. We can also do the hydrolysis step under basic conditions. If we have hydroxide instead of an acid, the hydroxide will attack the nitrile carbon, displace the electrons onto the N. That's the same kind of mechanism that we've seen as addition to carbonyls. We then have the N minus, which we can protonate from our water. That, notice, gets us that something that looks like an enol. It's an OH on a C double bond N instead of a C double bond C. So it looks a lot like an enol, and as such, it will tautomerize. So if we go through our standard tautomerization in base mechanism, remove the H from the alcohol, that gets us an O minus, whose negative charge is resonance delocalized to the alpha position. In this case, there's an N in our alpha position. If we reprotonate from that alpha position, we end up with an amide. So the nitrile under basic conditions will get hydrolyzed to an amide. The hydrolysis under acidic conditions gets hydrolyzed to a carboxylic acid. We've also done reductions on carboxylic acids, doing the reduction with lithium aluminum hydride to a primary alcohol. We've seen that before. It turns out that we can also reduce carboxylic acids not all the way to the primary alcohol, but to the aldehyde. And if you look at these reagents, these look familiar. Recall that when we had something like an acid chloride and we use this lithium aluminum tri-T-butoxy hydride, that allowed us to add a one equivalent of H minus to our special carbonyl and only get the aldehyde instead of doing further reduction like we got with lithium aluminum hydride. That same process is true if we convert our carboxylic acid into the acid chloride. We can then use, again, lithium aluminum T-butoxy hydride, do the single addition to our now what is our acid chloride, and that will get us to our aldehyde. So you can use this tricky conversion going from the carboxylic acid into the acid chloride, and from that exploiting our acid chloride for addition with, say, a Gilman reagent, the cuprate, or this lithium aluminum tri-T-butoxy hydride to get to aldehydes, when otherwise we would only be able to convert all the way to the primary alcohol. So you can see that there are some other types of molecules that keep cropping up in these conversions. We've seen acid chlorides or acid halides in general. That was one kind of our special carbonyl. that we could either add twice to using a Grignard or add once to using a cuprate, for example. Esters were the same way, another one of our special carbonyls that reacted differently from aldehydes and ketones. In our previous slides, we've seen making amides by hydrolyzing a nitrile under basic conditions. Here's our nitrile. We could also remember hydrolyze the nitrile to the carboxylic acid under acidic conditions. These are called carboxylic acid derivatives because their chemistry is closely intertwined with that of the carboxylic acids. Basically, they can be made from carboxylic acids, and it turns out that they can also be converted to carboxylic acids. So here are some examples of those structures. Isoamyl acetate. You can see this is an ester. It's a carbonyl carbon attached to an OR group. That's the flavor in banana oil. This is NN-diethyl metatoluamide. You can see the amide, the carbonyl C double bond O with the N group on it. That's an amide. This is, you can see, is a meta toluene metatoluamide. This is DEET, D-E-E-T, diethyl metatoluamide. Here's penicillin. This is penicillin G. There's all these different varieties of penicillin depending on what groups are attached. If you've got methyl groups or phenyl groups, things like that here. This is specifically penicillin G, but you'll see several functional groups. We've got an amide here, our carbonyl C double bond O with the NR group on it. And we've got a cyclic amide, this NC double bond O in the ring here. And we've got a carboxylic acid, the COOH. We've also got a thioether, this CSC, instead of COC. It's like an ether, but it's a sulfur, so we call it a thioether. So we'll take a few minutes to go over a couple reactions involving carboxylic acid derivatives, and then we'll stop and we'll continue part 2 next time. The first reaction that I want to talk about regarding carboxylic acid derivatives is something called the Fischer esterification. This is a reaction that makes esters, hence the name esterification. This is also the same Fischer who brought us Fischer projections in first semester. So the Fischer esterification involves a carboxylic acid reacting with an alcohol. And you'll notice how these two molecules come together. Our R group on our acid and the R group in the alcohol end up being the two R groups in our ester. And it's the OR grouping in the ester that comes from the alcohol. You can see that our R prime in blue came from our alcohol. That's over here in the OR prime in our ester. And the R from our carboxylic acid is in the carboxylic acid side of our ester, the carboxylate side of our ester. So here we have a 2-carbon carboxylic acid and a 2-carbon alcohol. So the carboxylic acid side will have 2 carbons and the alcohol side will have 2 carbons. Here we've got phthalic acid. We've got this dicarboxylic acid, and we're going to react it with excess methanol. So we should have our carboxylic acid side of our ester from the phthalic acid, and we should have a methyl on the other side, on the alcohol side. So here's our OCH3 from our alcohol. Now you'll notice here, they're very clear about the KEQ of this reaction. The Fischer esterification is an equilibrium process, and the equilibrium constant is very, very close to 1. Remember that the equilibrium constant can range from 0, where there is no reaction, and the equilibrium lies fully on the side of the reactants, and it can range all the way up to an infinitely large value, where the reaction goes to completion, and the equilibrium lies all the way on the side of the products. If the equilibrium constant is 1, that means that there's equal concentration of reactants and products at equilibrium. So from a scale of 0 to infinity, 1 is really, really, really small. So in this reaction, it's actually quite difficult to make product. Now, one way to get around that is we can use a drying agent such as magnesium chloride, magnesium hydroxide, calcium chloride. Those are common drying agents because they kind of bind to water and suck the water out of the reaction solution. Now, since water is a product, that means that our product will constantly be removed by our drying agent. And as such, the equilibrium will keep running forward to try to reestablish that equilibrium by making more water. So, despite the fact that our equilibrium is very close to 1, and without a drying agent, our reaction would stop after we've only used half of our reactants up. We can use a drying agent to constantly remove the water that's formed in this reaction, and that will eventually drive the reaction all the way to the product. And so we will have only our ester in solution and our drying agent clumped up as a solid bound to all the water. This also means that we can reverse the reaction. If we want to convert an ester back into the carboxylic acid and the alcohol, all we have to do is take the ester and add water. The more water we add to our reaction, the farther left the reaction will run. Here's the mechanism of Fischer esterification. It involves protonation of the carbonyl with an acid. Notice that this reaction requires an acid. Now, you might wonder, we're using a carboxylic acid, so why do we need to add acid to this? Well, it's because in the mechanism, the reaction only proceeds once our carboxylic acid itself is protonated. So we need some acid that is stronger than the carboxylic acid, such as sulfuric acid or some other mineral acid that will protonate our carbonyl. That will generate a resonance stabilized cation where there's positive charge on the carbon. That's what will get attacked by the alcohol OH, displace the electrons onto the O. And in our last step, we could remove the excess H from our alcohol. That gets us what is essentially the hydrate of an ester. Notice that we have our carbonyl has been hydrated. We have an OH and an OH. So that's a hydrate of our carbonyl, but we have an ester. It's an OR group there. So it's an ester hydrate. The next step will involve protonation of one of our alcohol OHs. That will get us water as a leaving group. We can displace water by bringing electrons down off of the O to make the double bond OH. We can then remove the excess H to get us our carbonyl back, and that gets us to our ester. So the alcohol basically adds to the carbonyl carbon, displaces the existing OH as water, and we're left with our ester, which is the carbonyl with the OR from the alcohol. There's an alternate method of esterification besides the Fischer esterification that uses a reactant called diazomethane. Diazomethane is CH2N2, and you can see in the mechanism here what it looks like. This is CH2N2. It's a neutral molecule, but it's a zwitterion. It's got positive and negative character as ions. And you can see that there is a resonance structure that puts negative charge on the carbon instead of negative charge on the nitrogen. So in the reaction of esterification using diazomethane, the negative charge on that carbon removes the acidic hydrogen from our carboxylic acid. That gets us our carboxylate, but it also gives us this methyl diazonium ion. It's a methyl group with N2. Now remember that N2 as a gas is a great leaving group. So what will happen is the carboxylate will attack the methyl group from our diazo, and that will displace the N2 as a leaving group. Now, notice that this is only useful for generating methyl esters. If we want something other than a methyl group here, we need more than just the CH2 on diazomethane. We need diazoethane or something like that. So you can modify this slightly to get different R groups on here, but remember that the more substituted this carbon is, if there are other R groups on here, the more difficult it is to make the negative charge. And so You'll have less contribution from the resonance structure that we actually need to do the reaction. So this will work for something other than a methyl ester. It only works really well for the methyl ester. One problem is that diazomethane is really hazardous. And so methods of like this are rarely used in large quantities. It's a great reaction if you're doing something in microscale because notice that there's no equilibrium. The reaction is always losing product as N2 gas, and so the reaction will always be driven forward. So it's a much cleaner reaction. You get almost no byproducts. But on a micro scale, it's great because we only have to use a little bit of diazomethane. On a larger scale, if we're going to try to be making tons of these methyl ester, we don't want to have to use tons of diazomethane. We can do similar reactions as we did with the Fischer esterification, but instead of using an alcohol to get us the ester, we use an amine to get us the amide. Notice that these are analogous reactions. The acid plus the alcohol gave us the ester, which is C double bond O. The carboxylic acid with the amine gives us the amide, which is C double bond O N. This reaction is a little bit messy because we have an acid in the carboxylic acid and the amine is basic. So you'll notice that in the presence of these two groups, we'll just simply do a proton transfer. The base will grab the H off of the acid. That gets us the ammonium carboxylate salt. And this is relatively stable. It just kind of sits there. But if we add enough heat, those two salts will condense and we'll get the amide and we'll boil off water. So again, not the ideal method for formation of amides. There are other methods of amides that are better. I'm going to show you that in the second half of this lecture. The problem is that we make the ammonium carboxylate salt. It's easily formed but difficult to convert. It requires high heat because we have to drive water off. And therefore, the reaction requires temperature resistant groups. If there are anything else on our amine, our R group on our amine, or the R group on our acid that are reactive under high temperatures, or say unstable, decomposable under high temperatures, this method for making the amide is not feasible. So we'll continue in part 2 with more reactions of carboxylic acid derivatives.